Hello, everybody. Welcome back to the Feynman technique. Uh, Today we'll be taking a look at this integral. Um, it looks similar to one I've done before, in which I evaluated the same integral, except the denominator of the integrand was 1 plus x squared. Introducing 1 plus x to the fourth instead makes it quite a bit more difficult. But we're still going to be solving it with classic Feynman integration. Um, so let's go ahead and get started. All right, so we have our integral labeled I. Let's go ahead and do the usual first step, which is to create a function of t that closely resembles our original integral. In this case, what we're going to do is we're going to introduce a t to the fourth here. I introduce, instead of t, I'm going to put t to the fourth. I think it makes it a little bit, makes it work out a little bit nicer. You don't have to work with square roots as much. So this is what we're going to be doing. Okay, so we'll notice from here that this implies that f at 0, well, if we plugged in 0 to this, we'd get natural log 1 on top. That would give us 0. Okay, and to recover our original integral, we need f at 1, because of course 1 to the fourth is 1, and that would recover our original constant in front of our x to the fourth term there inside the natural log. All right, great. So we've set up our function of t expressed as an integral and provided some boundary conditions on it. Now what we need to do is differentiate our function of t with respect to t in the hopes that doing so will make it easier to solve. All right, so let's go ahead and take the derivative with respect of t, which, of course, as you know from watching this channel, what you do is you just differentiate that integrand with respect to t, and then have the same bounds of integration and integrate with respect to x. So this is going to be equal to the integral from 0 to infinity of, let's see, well, we're going to get 1 over the thing inside the natural log. So that's this part right here. And then, of course, we'll also have this part since it's constant. And then we'll have the derivative with respect to t of this whole part, which is just the derivative with respect to t of this whole part. So we're going to get 4t cubed x to the fourth dx. So there is our function of t. Now, the next step is, let's see, we could do partial fractions right now. In fact, yeah, I think that's what we're going to do. Now, I'm not going to be showing the steps for the partial fractions because that's kind of a mess. So I'm just going to jump right to what it's going to be. I'm going to state this. By partial fraction decomposition, this is just going to be equal to this. Again, I'm not going to actually show the steps to do that. It's partial fraction decomposition. It's just a computational process, so I don't want to really spend a whole lot of time on that. So let's go ahead and rewrite our f prime of t. Well, we can replace it. We can replace it like this. Okay. So this is a constant with respect to x, and we can bring that directly outside the integral. And then let's go ahead and split this into two separate integrals. So this one will contain the second part, and this one will contain the first part. Okay. Now this is one that a lot of you probably recognize already, but I'm going to be using a formula to solve it. The formula I'm going to be using to solve both of these integrals is this. Now, that seems like a mess, but you'll notice both of both of these integrals are of that form. So what we want to do is let's use it on this form right here. Okay, well, that's going to be equal to this, where we fill in the appropriate constants. By the way, this is what I call the extended universal Mellon-Barnes integral. It comes from the integral of 0 to infinity of 1 over x to the t plus 1 dx, which I've proven. And I think I also did a video on this. But basically, it just accounts for every possible type of constant in it. So now we just need to match them. And again, a lot of you probably already know what this integral is, but we're going to use the formula on it. Okay, so what is our d? Well, that's our d corresponds to the power on x. Okay, in the denominator. So that's going to be a 4. So we're going to replace all of our d's with 4s. Okay. Now, what is our s? Well, that corresponds to the constant in front of our x term on top. We have no x term on top, but we kind of do. We have an x to the 0 on top. So our s is going to be 1. So let's find all the s's and just put that. Okay, so that's it. That's all there is for s. All right, now what do we need? Let's figure out what our t is. Our t is the coefficient in front of our x term in the denominator. So that's going to be 1. So this whole thing is going to be 1 to the something, which is just going to be 1. So it goes away. Okay. So what do we have left? C. That's our term in front of our x in the numerator, which is 0. So we're going to get a 0 there and a 0 here. So this part is sine pi over 4. And what's our u? Our u is 1. So, of course, this whole thing becomes 1. Let's bring this pi on top. Let's bring this 4 in the bottom. Okay, now I could write this in terms of square roots. I'm not going to. This is fine. All right, so now let's go to our other one. Okay. Now, this is going to be a little bit tricky since we have t terms. Oh, luckily, our t term down here corresponds with the t term up here. So this is going to be equal to, and just for fun, let's fill it out step by step again. So our t term is no longer, let's see, what is our t term is actually t to the 4th. Okay, so our t term is actually t to the 4th. So what that's going to give us is just a 4 right in front of here. If we have t to the 4th to the negative c plus 1 over d, that's just going to be this. Okay, again, our s is 1. Yeah, our s corresponds to 1. Our d corresponds to 4. Yep. D corresponds to 4. So 4 and 4 and 4. All right. We already figured out what our t was. Now we need our c. Our c is going to be 0. So it's going to get, what was it before? 0. So that's just going to be 1/4 times negative 4, which is just negative 1. Okay. Our c was 0. That's right. But also our u is 1. So without even doing any of the other stuff, this is going to be 1. All right. So again, our c was the exponent on x in the numerator, so that is 0. So that's still sine pi over 4. Let's bring the pi up top. We'll bring the 4 down bottom, and we'll also bring this t to the bottom. So there we go. All right, so now we can plug those values into our f prime of t. So f prime of t is equal to this. Well, we already know, or we just determined, that this integral was this, and this integral was this. Okay, so now let's do some simplifying here. Let's see, this 4 is going to cancel. This 4 is going to cancel. This is a constant, so let's bring it out front. Let's see, a t is going to cancel upstairs with this t. The 4 is going to cancel. And again, we're going to get a constant out front. So let's go ahead and factor out our constant term right here. There we go. So there's f prime of t. Now we need to get back to f of t. So f of t is going to be equal to, well, let's see. It's just the antiderivative of this thing with respect to t. And both these integrals are not so bad to solve. You can solve them. This one is quite easy to solve with the substitution. U is equal to t to the t squared. This one's a little bit trickier. You need to break out some tricks up, but it's not anything beyond the level of calculus BC. So I'm not going to be showing that. I'm going to be jumping directly to what this is equal to. So f of t is going to be equal to this. And that, it turns out, is equal to this. Well, we're going to have this constant term, and then times the antiderivative, which is this, according to online integral calculator. Okay. So, let's see. Oh, and then of course we have plus c. Now let's clean this up a little bit. We don't care about the absolute values very much because we're plugging in 1 and we're never going to get a negative number in there. We might, however, get a 0. In fact, we will get zeros, but it's never going to go negative, so I'm going to remove the absolute values. And then we're going to simplify. Let's use the properties of logarithms to bring this natural log, this t minus 1, into the denominator of this natural log, t minus 1. All right. And then we will bring this upstairs on this natural log. Okay. So now you'll notice that this can be broken up into t squared plus 1, t squared minus 1. And this can be further broken up into t squared plus 1, t squared minus 1. I'm not going to write t plus 1, t minus 1. I'm just going to leave the t plus 1 because the t minus 1 is going to cancel this. All right, great. So there's our f of t. Alrighty. Let's see. So now we need f evaluated at 1, I believe. Yeah, we have I is equal to f evaluated at 1, which is equal to... Oh, I'm sorry. We forgot something. We need to account for this constant of integration. So let's see. F of 0 is equal to 0. Well, that's going to be equal to this when t is 0. Okay. Let's see. This part is going to evaluate to 0. Arctangent 0 is 0. And if we plug in 0 for t, we're just going to get 1 times 1 times 1, and then take the natural log, which is 0. So we're going to get 0 is equal to c. So we have c equals 0. So f of t is just equal to this. So now I is equal to f at 1, which is equal to this. Tangent 1. This is just a 2. This is just a 2. This is just a 2. 2 times 2 times 2 is 8. Well, let's just write that as 3 natural log 2. Moment of truth. Let's see if this equals what it should equal. Yes, it does. Let's go ahead and copy this integral down here. And you can see those numbers do in fact match. Now let's clean this up a little bit. Let's see, arctangent 1 is pi over 4, so 2 times that is going to be pi over 2. Sine pi over 4 is square root of 2 over 2. Let's bring this 2 on top. Bring another square root of 2 up here to bring this 2 down here. 2's cancel. Let's see. I don't like the pi over 2 here, so let's multiply inside by 2 and divide by 2 on the outside. So this is actually a 6, and this is minus pi. Let's see. And then let's bring this outside to make this an 8. So we have square root of 2 over 8. Let's put this pi out here just to make it nice and clean. Pi square root of 2 over 8 times quantity 6 natural log 2 minus pi. We'll even get rid of those parentheses just to make it nice and clean. And there we go. All right, guys. I hope you enjoyed that long video, and we'll see you next time.